glad to start on time today, which is quite unusual. We just had an excellent ITC colloquium by Ram Sari, who's sitting over there. Basically, if I had to summarize it with one sentence, it's that hot Jupiters are batteries. Right? Yeah. They're heated from one side, the other side is cold, then current flows and heats them up, which makes them batteries. And we'll hear from Ram. Actually, we will not hear from you.
Today? No,
not today. At a different lunch. Yes. Our first speaker today will be Morgan May from Columbia University and Brookhaven National Lab. And as you can tell, he has a very good title, which basically says that experiments in the lab are relevant for cosmology. And we'll hear more about that in a few minutes. After that, we'll hear from our own Rosanne Stefano over there that will tell us why globular clusters may be green, right? Maybe green. She will talk about the globular clusters as cradles of life and advanced civilizations. And after that, we'll hear from our CFA colloquium speaker, Keith Gendreau. Gendreau. It's a French-sounding last name. Is Keith here? Oh, over there. Did I say it correctly, Keith? It's okay. He's visiting us from Goddard, and at the CFA colloquium he'll talk about NICER, which is a new mission that will primarily probe neutron stars. But here at lunch, he will talk about the modulated X-ray source for X-ray emission calibration. And finally, we'll close with Olek Sadowski, who is a postdoc at MIT. Used to be here in the ITC, and he will talk about thin accretion disks are stabilized by a strong magnetic field. Morgan.
Thank you. I'm going to tell you how measurements of CCDs in the laboratory can be used to calculate the cosmological parameter bias for a survey, and emphasis is on LSST, which is a future survey, the telescope being constructed in Chile on a mountaintop. This shows the focal plane of LSST, which consists of 21 rafts of 9 CCDs each, and here's the image of the full moon on the focal plane. The work was done in collaboration with these colleagues, and I emphasize Andrea Petri, who is a graduate student at Columbia. Doing cosmology by weak lensing, we want to compute the dark energy parameters, other cosmological parameters, from the weak lensing power spectrum. This requires precise measurements of galaxy shapes to search for correlated apparent shape changes caused by intervening matter. Hence the concern about imperfections in the CCDs, especially those not correctable as quantum efficiency. So I'll talk mainly about two widely discussed sensor imperfections, which were a source of concern. Now the silicon for the CCDs is grown from a melt, and it grows cylindrically, so impurity concentrations tend to vary in a cylindrical fashion, and that results in patterns which look like tree rings. And those impurity gradients cause transverse electric fields. Pixel size variation is due to errors in the masks that are used to fabricate the CCDs, and both of these imperfections can be seen in the flat fields when the detectors are subject to uniform illumination. And neither of them is correctable as quantum efficiency. So here's a sensor with uniform illumination. We've cut out regions where there was dust on the lens, and there are shadows of the dust on the lens, but you can see clearly the tree ring pattern in the flat field. And when we focus on on a small region and magnify it, you can see the pixel size variation in these vertical and horizontal striations. When we average the pattern, you can see a very regular variation in pixel size.
So what's the amplitude of this?
Well, the amplitude of the flux modulation is 0.01%. Yeah. The pixel size variation is about 5 times larger magnitude. So from now on, I'll talk about the tree rings, and at the end, I'll tell you the conclusion about the pixel size variation as well. So the same transverse electric fields that cause the flux modulation in the flat field also causes displacements of stars and other, and we can calculate that displacement from the flux modulation in the flat field. And from those displacements, we can calculate the distortion, the shear, and the magnification, the convergence of images, which is caused by that displacement. And it turns out that the convergence and the shear are about half the amplitude of the flux modulation. So here is the pattern of spurious shear on an LSST CCD. The CCDs are cut out of four are cut out of a wafer, and the corner of the CCD lies at the center of the wafer. And so here's the pattern of spurious shear. Now here we've put together many CCDs into a raft, and then we put together many rafts into a focal plane to calculate the effect. Now you'll notice that the spurious shear alternates sign from tree ring to tree ring on the tree ring scale. Now this has a favorable consequence in terms of the two-point correlation function. When we measure the two-point correlation function, we average over pairs of galaxies at fixed separation in different orientations and placement. So the alternating sign of the spurious shear leads to a large cancellation in the two-point correlation function. So the effect of the tree rings is far less than you would expect from the magnitude of the spurious shear. And here is the this is the two-point correlation function in the prototype CCDs and the typical magnitude is far less than the lensing shear. Now, we go on to calculate the bias. The bias is the shift in the cosmological parameters if spurious convergence is present but uncorrected. So we can use cosmological simulations and calculate the lensing. Here it's easier to work in convergence. Convergence in a grid of cosmologies. And if we add the spurious convergence to the lensing convergence in the fiducial cosmology, we can then see what the implied cosmological parameters are, and that gives the bias. Because we're working in parameters derived from the lensing power spectrum, we can use a public emulator for the power spectrum and do the calculation more easily. If we go on to, I'll get to that later. I'm at the conclusions. So for LSST, the bias due to tree rings and pixel size variation is negligible for cosmological parameters derived from the lensing power spectrum. So here's the bias due to tree rings in the omega matter W sigma 8, and due to pixel size variation. For example, for W, we hope to make sub-percent level measurements, and still these biases will not be a problem. So in the future, we will apply these approaches to calculate biases due to other CCD imperfections and systematic errors. And also, we are interested in cosmological constraints from non-Gaussian statistics. The power spectrum only contains a small fraction of the perhaps half of the information in the convergence field, and considering 3-point correlations or shear peaks, we can obtain more information, and we will calculate how these sensor imperfections would affect these other analyses.
Why can't you study the CCD to a very high precision so that you can correct all the error introduced from it, if you know the CCD?
Yeah, well, that certainly would be, in principle, possible. For LSST, we have a 30 gigapixel camera, and to make flat fielding is a normal correction, but to make shape corrections on every pixel it's better if you don't have to do it. No.
In the early days of CCDs, Tony Tyson would do multiple exposures with slight offsets,
Dithering.
so that the same pixel wasn't on the same spot in any two exposures.
Yes.
Doesn't that wipe a lot of this out, if you can do it?
Well, we will, LSST will have hundreds of exposures of each patch of sky, and they will be dithered. I was pointing out here that there's a natural effect that doesn't rely on dithering, just because when you take the 2-point correlation function. But yes, well, Tony is a colleague, and he emphasizes this point to us today. Yeah, thank you.
I'd imagine this has a very strong dependence on the ratio of the expected point spread function from seeing compared to the size of the pixel. Is that right? I mean, if your pixels are small compared to the point spread function, this must essentially vanish.
It depends on the size of the point spread function relative to the spatial scale of the things that Moni's talking about.
Yeah.
Right.
Obnoxiously light at the DSF scale.
Yeah, and thank you. The tree ring scale, the scale of variation for tree rings is about 100 pixels. So this is much larger than the point spread function. But the pixel size variation is at that scale.
What's the Gendreau scale? 0.2, so it's a different fraction of the galaxies.
Of course, in addition to LSST, W first has as one of its objectives doing cosmology with weak lensing. Have you looked for the effect of imperfections on detectors other than CCDs?
Well, one of our collaborators on this work, Andres Plazas, is at JPL, and he's working on W first. So he's going to apply this to W first detectors.
Other questions? Looks like everything was clear. Thank you very much.
Okay. So while Olek was here, Olek Ray, who joined us for almost a year recently, we asked ourselves, what would it be like for members of a civilization like ours to live in a globular cluster? Well, it certainly would be bright. But what we were interested in was the fact that the incredible densities, up to 10 to the 6 stars per cubic parsec in the center of some clusters, means that nearest neighbor distances could be very small, tens to 100 times smaller than they are in the solar neighborhood. And so that reduces round-trip communication times. It reduces possible travel times, if there's anyone there to communicate or to travel, which we certainly don't know. I'll note here that for a round-trip distance with the one-way separation being 1,000 AU, the time for that communication is actually shorter than the time it took the British to communicate from Staten Island to London in 1776 to tell them that the Declaration of Independence had been signed. So our idea, this isn't the research that we did, but it's what motivated us, so this is still the motivation part of the talk, is that if these small distances would allow a civilization in a globular cluster, should one exist, to establish independent, self-sustaining outposts on a time shorter than might occur in our region of the galaxy, this would be a big step toward ensuring the survival of the civilization, because no one catastrophic event could wipe it out. So we became interested in this combination of high density and yet possibly survivability. But the first question, and this one has been addressed by other people, is whether globular clusters host planets. And this is a very rich area. I'm just going to make 3 comments. That the Kepler data has been very well analyzed and shows that with a fairly high frequency, M dwarfs in the field have within their habitable zones planets that are comparable in size to or slightly larger than the Earth. Planets have been found in open clusters, and one planet has been found in a globular cluster. It's often referred to as Methuselah. It orbits a millisecond pulsar, which we think has been spun up by mass accretion from its companion, which today is a helium white dwarf. Methuselah is in a very daring orbit. It's 23 AU from this inner binary, which means that since interactions among stars are common in globular clusters, this is a very perilous orbit and almost certainly will not survive. Now, if you have planets in the habitable zone of low-mass stars, however, these habitable zones are smaller, meaning that a passing star has to come closer in order to disrupt the system. This decreases the rate of disruption and increases the average lifetime of the systems. Now we're getting to what Olek and I did. Okay, so we wanted to find out, in a typical globular cluster, are there places where it's dense enough for there to be relative proximity, say within 10 to the 4 AU between nearest neighbor stars, and at the same time not so dense that planetary systems in the habitable zone get destroyed. We know that at the center, systems are likely to get destroyed, at least in some clusters, and that as you go out, the cluster gets more diffuse. So our question, and what we wanted to quantify, is there a sweet spot, someplace between these two extremes, where habitable zone planets can survive? To answer that question, we modeled globular clusters. We used a Plummer model because it gave us the very nice opportunity to consider many clusters and vary their properties by varying the total cluster mass and the scale factor, which can be related to the concentration. And these were important for us. With the model in hand, we could compute the average lifetime of habitable zone planetary systems as a function of mass of the star and as a function of position in the cluster. we could then seed the cluster with stars. And we did that for a realistic population with an age of about 12 gigayears. The spatial distribution of these stars was consistent with the mass distribution of the Plummer model. And then we computed the local densities and ambient fluxes at each point in the cluster. And this graph shows you one of our results. This is for a cluster that is not particularly concentrated. And in the top panel, we see the log of the survival time of habitable zone planets versus the log of position within the cluster, distance from the center. Now over here, this curve corresponds to a 0.1 solar mass star. It hits the axis above the Hubble time, meaning that habitable zone planets around such stars can survive any place in this cluster for more than the Hubble time. The same is not true for massive stars, and this is the point at which a 0.8 solar mass star would be able to keep its habitable zone planets for about 4.5 billion years. As I said, this isn't a very concentrated cluster. In the second panel, we show the log of the nearest neighbor distances, again, versus distance from the center. And the average distance goes down or goes up above 10 to the 4 AU at around here. And so for a 0.8 solar mass star, the sweet spot is an annulus that's about this big. And of course, it's different for different stellar masses. Now, let's change the cluster. As we go to a more concentrated cluster, things can change dramatically. For this one, the survival time for a 0.1 solar mass star is under 10 to the 9 years in the cluster center, and even such a star, denoted by this red line, has to be further out in order for the system to survive for 4.5 billion years. This actually is the habitable zone of a white dwarf. These were considered by Eric Agol. However, in such a cluster, because it's more condensed, you have sustained high densities much closer to the edge of the cluster. So the sweet spot moves out. In general, if looking at all of the results for various clusters, there's a balancing act between high concentration and low concentration, high cluster mass and low cluster mass. Some planets in habitable zone orbits will be ejected from those orbits, and some planets in wider orbits will certainly be ejected from those orbits. So now the question is, are there civilizations in these clusters? And of course we don't know. But what we can do is we can use the Drake equation to compare the globular cluster environment with the galactic environment. Now, this represents all the factors we normally associate with the Drake equation: the lifetime, the probability that a star that a planet will have a communicating civilization. If these factors are roughly the same in the two environments, and we can discuss that, then the number of communicating civilizations scales with the number of stars. So let's just pick a number, let's say 10 to the 6. If over an entire Hubble time in our galaxy at one time or another 10 to the 6 communicating civilizations formed, we would expect in each globular cluster a few such civilizations would have formed. Now let's consider a short lifetime. If the lifetime of such civilizations is 10 to the 4 years, that's about 100 times longer than we've had a communicating civilization, according to most estimates, then in our galaxy, we very likely are alone right now. So you can look around the room and say hi to the communicating creatures in our galaxy. In a globular cluster, if outposts were not formed, you'd expect no civilizations in globular clusters. But if outposts could be formed, even from one of the civilizations that arose in a cluster, it could have a very long-lived civilization present today. In the long lifetime limit, let's take it to be a Hubble time, of course our galaxy is also rich in civilizations, as are globular clusters. So in either case, if we're looking for life within galaxies, it also makes sense to look, whoops, there we go, within globular clusters. Which clusters? Well, we analyzed the cluster parameters associated with recycled pulsars. So these are the types of systems that we find Methuselah orbiting. And what we found is that this balancing act between high and low concentration occurs for these systems as well. So of course, one might be interested in any globular cluster, but this list is ordered according to the number of recycled pulsars we've discovered in the globular clusters, and it may give us a starting point. Now, I'm going to conclude, there's only one point on this slide that I haven't made before, which is, while we've just mentioned that globular clusters with multiple millisecond pulsars may be good places to search, what I haven't mentioned is that millisecond pulsars, with their very precise timing, are also wonderful for navigation. And there's a whole literature on using them for navigation, using the ones that are in other, in globular clusters for our navigation. But if you're in a globular cluster, you have a ringside seat for this. And what you may not know is that there's actually even a patent on this navigation system. So thank you. Mm-hmm.
Over time, in sample different regions. So the question is, did you look with an n-body simulation into the question of how other stars avoid?
This is a crucial point. This is a very important point. We did not do an n-body simulation. As you know, you can do n-body simulations, and the results may not always correspond to exactly what happens in the cluster, because the results depend very much on things like binarity and so forth. However, what we did do is we specifically included mass segregation. And so what that does for you is the more massive stars tend to congregate toward the center, and they will actually spend more time there and are less likely to survive. So we took that into account, as well as the fact that the less massive stars tend to float to the top in a way. So that does not destroy the existence of the sweet spot. What you really want to do is to integrate over the time a star spends in each region and to see whether it survives longer than the time it would spend in that region. So yes, we have begun to look at that. And it seems as if no matter how one approaches it, this general result is robust. Will there be changes by 10%, 20%? Yes, there will be.
I was just wondering if you had coordinated with any SETI observers to see whether they looked for fish that are looking in these globulars.
We're working on it. We're working on it. I think, the question for globular clusters is SETI searches are, in a sense, passive searches because they're so far away. So we're looking for signatures of advanced civilizations without being able to have any kind of two-way communication. So Kevin Hand, I think you may remember, he visited and gave a physics colloquium a few months ago. And so we've started talking not only about that, but about free-floating planets, which also come into play in globular clusters, and were part of the reason that we also made sure to compute the local fluxes.
To your point, Erwin, I think some of the earliest SETI searches, certainly done by Arecibo, were tour globular clusters. Also, I think Keith this afternoon will be talking about pulsars as a navigational tool, even locally.
So it fits in. Yes, yes.
My question is this: I wonder if there's a process that works against the evolution of advanced civilizations and globular clusters in the following sense. If planet formation is similar there as to what we observe locally, certainly in our own solar system, then these systems are surrounded by a halo of cometary debris, such as the Oort cloud. And we've always thought that the raining down of these bodies onto the solar system can be caused by perturbations due to a passing star. Now you're in an environment where these perturbations are on steroids. And I'm just wondering if you thought about the environment of forming planetary system in regard to the number of these debris objects that would be raining down due to the perturbation of all these stars.
Right. Well, of course, in a cluster, on the other side of that is the fact that you would not have disks that are as large as in the solar system. So you may actually wonder whether planets can form in these dense environments at all. Because we are now beginning to find them in open clusters, and many open clusters are very dense, it certainly doesn't rule out planets in globular clusters. But what you're talking about is actually, I think, the frontier. It's just like when SETI first started, we didn't know about planets at all outside of the solar system. Right now, we know very little about planets in globular clusters, and I think that is the frontier, to study planets, and you can use lensing to look for free-floating planets, and you can use the techniques that are being used today to look for planets on the outskirts of clusters. HST observations have been used to eliminate the possibility of hot Jupiters at the center of 47 Tuc, for example.
Just to be clear, I don't doubt the possibility that planets could form. The question is, would life have an opportunity to exist unperturbed long enough in order to evolve into something advanced before bodies slammed into these planets?
Right. It's a very different environment, and so it'll have much smaller disks, yet the interstellar medium may be more dense, especially to begin with in early times. So these types of calculations really need to be done, I think. Now, the interesting thing, though, is that in a cluster environment, less massive objects, like these bits of rock, are more likely to find their way out to the outer parts of the cluster. Mass segregation is a very important effect. So I think it's really a fascinating field for future research.
It's not clear to me that it would be on steroids, as you're saying, because the passing stars will clear it early on, and then it's not clear if the process will continue, because planet formation only took place once when the star was born, and the passing stars destroyed the outer bodies that are formed, and then it's not clear, so we have to calculate this.
What we keep in mind that the globular clusters themselves evolved a lot during their lifetime because they pass through the disk, they get short, so there could be other phenomena that shape them and started denser than they are right now.
That's certainly the case. I really think it's very interesting to try to understand that evolution. However, I will point out that the existence of Methuselah is an important piece of information because M4 is not a high-density globular cluster, and if the only planet in M4 happens to be one that went through this very unusual evolution to be in a very unusual system, I think we would have very good chances of winning the lottery. So I think it's absolutely clear that M4 has other planets. And I do think that this is the area that over the next 10 years I expect there to be a good deal of progress. We'll find out whether globular clusters have large sets of planets within them.
This is certainly very stimulating and interesting work that you've done and quite a lot of connections. So we also look forward to learning more about whether these systems have planets and whether, of course, they have life. Thank you very much.
All right, how are you? Oh, that's great. Hi, I'm Keith Gendreau. I'm from NASA Goddard. I'm a PI for NICER. I'm going to talk with you about an X-ray source technology that we've been developing at Goddard to support a number of X-ray astrophysics missions, and we think it has a broader application to the general community as well. Our original motivation for building this X-ray source, the modulated X-ray source, or MXS, was we have a long-term vision, at least I do, and some people at Goddard and a number of people in the community, to build a mission called the Black Hole Imager, an X-ray interferometer that could resolve the event horizon of supermassive black holes. It's way out there, and it involves technologies we don't quite have, so we're making technology roadmaps. And one of the important technologies that we need to have is a method of, to resolve the event horizon of a supermassive black hole, we need an aperture of order a kilometer working in the X-ray band to get micro arcsecond type angular resolution. And we can't do that in one spacecraft, but it's going to involve multiple spacecraft, and so we've envisioned architectures where we have swarms of mirrors separated over a kilometer that direct X-rays to a detector spacecraft many, many thousands of kilometers away where the image can be formed. And one of the important technologies that we need to develop is how do you understand the formation flying orientation of these spacecraft and the relative positions, because it's going to clearly affect the X-ray interferometry performance. And so you need beacons. And when you get into this, you quickly realize that optical beacons are not good enough, radio beacons are not good enough. To align an X-ray interferometer, you need X-ray beacons. And so we started thinking about X-ray sources that we could use. And I don't mean X-ray sources like radioactive sources, I mean sources that are much brighter. So electron impact sources, we accelerate electrons into a metal target and you produce X-rays. We launched these things where we're into making instrumentation that's very robust for rough environments. And so we got into an idea of making an X-ray source that's photoelectrically driven, so you have no hot filaments like you see in medical X-ray tubes. This is no moving, it's a much more robust source. And so using photocathodes to generate the electrons that you would accelerate into a target to make X-rays. This was our original concept in a cartoon I made a long time ago. The idea is that you have light coming from, say, a light-emitting diode, an LED that would shine on a photocathode, generate photoelectrons. You would accelerate those photoelectrons into a target, and then that's held at very high potential, and X-rays would be produced. And it's a very simple concept, but no one's really made these things. And so we've made these things. You modulate the LED, you modulate the photoelectrons, and you can produce very crisp and very finely controlled X-ray flux modulation. This concept is actually very similar to what you see here is going to be used on Astro H to provide the gain calibration. I'll talk about that in a moment. But we've, over the years, have improved the concept so that it's even more robust. This previous concept for this to work, it relies on photocathodes having very high quantum efficiency, so that for reasonable wavelength LEDs, you can get a reasonable number of photoelectrons generated to produce X-rays. Unfortunately, the best photocathodes for this tend to be these bialkylide photocathodes. They have 10 or 20% quantum efficiency, but they're very difficult to work with. They get poisoned with oxygen just very, very quickly, and a little bit more challenging to make. We've come up with a more robust source where we can use much more stable photocathodes. We use metal photocathodes, typically aluminum, copper, zinc, to produce photoelectrons. The photo efficiency of these photocathodes is much lower, but we can compensate for it with very inexpensive and high performance electron multipliers. And I'll show you this. We can make a package which is very small and robust with this. And again, it basically works the same. Light stimulates photoelectrons, which we multiply. Our multipliers have gains of about 10 to the 8, which produces enough electrons to make a bright enough X-ray source. and we accelerate that into a target producing X-rays. And just to kind of reiterate, compared to hot filament X-ray sources, our big advantage is that we can do really arbitrary modulation. So medical X-ray tubes or usual hot filament X-ray tubes, you have thermal time constants which control the X-ray flux output. With a photocathode-driven X-ray source, we can do very crisp turn-ons and turn-offs and actually arbitrary shapes. So we've been kicking this around for a few years. Our very first modulated X-ray source was made 10 years ago, and it was about a 40-pound thing and relatively weak. Over the years, we've come down to something that can fit in my hand. It's about 3 orders of magnitude, 4 orders of magnitude brighter than the original one, weighs 160 grams. And it's TRL-6, which means we can launch this on rockets and calibrate things with it. So our applications in astrophysics are usually X-ray detector calibration. There's a number of material science applications. There's medical applications, which we're now starting to work with. And there's some more interesting applications that I'll touch on briefly. One thing about it is this X-ray, there are no X-ray sources out there that you can control so easily in terms of flux, and so we really think this is opening the time domain in X-rays. So first I want to talk about in-flight calibration of X-ray missions. So this is a plot from Suzaku, the old, Astro E days. This is a microcalorimeter. Goddard makes microcalorimeters, which have extremely high energy resolutions. Our Astro H is going to be producing microcalorimeters that have an energy resolution of about 2 electron volts. The thing about microcalorimeters is to achieve that very high energy resolution, you need very good gain knowledge. So these microcalorimeters are held at about maybe 50 or 60 millikelvin, and we have to stabilize the temperature of those microcalorimeters or understand the temperature of those microcalorimeters to about a microkelvin. And only picowatts of stray radiation can throw you off. And so they get around that by putting a radioactive source or an X-ray source in there to track the gain. And in the Astro E days, the microcalorimeter that was flown on Suzaku had only iron 55 as an option. And this plot shows with the mirror and detector response for Suzaku what the microcalorimeter would have seen for a thermal plasma, a 5 kilovolt thermal plasma at various flux levels. The black curve, the red curve, and the green curve are basically the same spectrum, but just lower and lower fluxes. And the dark blue curve is the source that's been sized in the iron 55 to actually track the gain, so Suzaku could have realized that energy resolution. And what I want to point out is that iron 55, it's always on, and you get these nice bright calibration lines to get your gain, but those lines are very close to interesting astrophysical lines. And on top of that, the way all detectors work, including microcalorimeters, you have an electron loss continuum where the process of how those X-rays interact in the detector yield a background which is always there. And by comparison, the expected particle background for Suzaku for the calorimeter is several orders of magnitude lower than just the electron loss continuum from the radioactive source in Astro E. And so if somehow this source could come and go, you realize for the science a much higher sensitivity. So a few orders of magnitude reduction in background if somehow you can control the X-ray source. And so that's what the modulated X-ray source provides. We didn't have this in time for Suzaku, and unfortunately our calorimeter failed to work on orbit. But Astro H is coming up and launching next week, and it's actually flying a modulated X-ray source, a variation of which is being made by the Dutch Esron. And they should be able to achieve a situation where this X-ray source is on for, say, a millisecond every second, and they know they get the calibration they want when they need it. A little closer to my heart right now, I'm working on the NICER mission, which is an X-ray timing mission, and fundamental to that is be able to do time resolution and timing calibration. And with a modulated X-ray source, we have the possibility of pulsing X-rays relative to a detector. This is an early picture of an engineering unit we had a long time ago. We could pulse X-rays in a narrow spot on our silicon drift detector here and move the source around and measure the delay time between the pulsing command of the X-ray source and the measured X-ray signature, which allows us to measure the drift velocity, which is key for NICER to achieve its timing resolution. On the Praxis mission, or the Goddard X-ray polarimetry mission that's being developed right now, it's a photoelectric polarimeter in one dimension. The imaging is done by timing, and that depends on the drift velocity of the gas in that photoelectric detector. And again, we're using a modulated X-ray source to measure that drift velocity. This is a picture. We provided an X-ray source, a modulated X-ray source, to our colleagues at MIT that are building the detector subsystem for NICER. And this is, so what they did was they took an X-ray source, a modulated X-ray source, fluoresced a target, pulsed it at 10 nanosecond wide over a 600 kilohertz rep rate, and fluoresced X-rays were produced, which give us gain and energy resolution in one axis in a folded plot versus time resolution in a different axis. So it's actually very useful. To touch on the previous talk, NICER is also going to be doing a pulsar navigation demonstration, and with our modulated X-ray sources, we can do arbitrary light curves. So we've been able to simulate, we can simulate the light curve that you would expect from a millisecond pulsar and put into that signal all the Doppler and phase shifts that you would expect if you're looking at this pulsar from a spacecraft in a particular orbit. Those X-rays can then strike our detector, and we can execute our pulsar navigation algorithms and work out our navigation solution. And I think I'm a little over time, so I'm not going to spend any time on this, but there's a number of actually interesting non-astrophysical applications, and we're working with Mass General Hospital right now to make ultra-low dose X-ray medical imaging devices using the modulated X-ray source. I like to have these stories because when I go home at night, my wife wonders why we waste money on astronomy, and I like to tell her that sometimes, looking for black holes can yield a technology which touches you in a more direct way. But so I actually passionate about this type of stuff, and so we are working on this type of technology enhancements as well.
What's her reaction?
It's slightly better. I've got a hard scale to work for. Another thing that we're doing, we've actually, with X-ray sources that we can modulate, we've been able to encode information. And so we have, in my laboratory at Goddard, come by and visit, I'll show you. We've been able to transmit data by X-ray modulation. We've done up to 100 megabits per second. I think this is the first in the world to be done this way. And there are a number, there are non-NASA entities that are interested in this type of technology, which we're trying to tap into to see if we can get them to support some of the additional technologies that I want to develop for black hole imager, including diffractional emitted X-ray optics, where a modulated X-ray source coupled with a diffractional emitted X-ray optic will lead extremely tight beams for secure point-to-point communication. And by the way, they'd be fantastic for doing very high-resolution X-ray imaging. And I'll end with that. Thank you.
If you were in the private sector, you would have gotten so much money from that because your research on astronomy. I guess NASA does not make profit out of it.
Actually, they allow us. So actually, we did get a patent on the X-ray source. We don't have a patent on the pulsar navigation.
Can you explain why you need calibration so frequently?
So in a microcalorimeter, for example, if you're trying to achieve very high energy resolution, what we're trying to do is hold our detector at a very stable temperature around, say, 70 millikelvin. And if you start to think about what it takes to hold something at 70 millikelvin above absolute zero, you realize that almost anything can make that temperature change a little bit. And we're measuring energy just by temperature changes at the microkelvin level. So if you build enough of these things, you see that over reasonable time scales, tens of minutes, these detectors will drift in temperature by an amount that you need to correct for. And so that's why you size your iron 55 source to be as bright as it is. And there's a consequence, which is that electron loss continuum plus the other background terms associated with the source. So does that answer your question?
We all look forward to your plotting later today.
Okay, thank you. Oh, I'm sorry.
Okay, so in our galaxy there are hundreds or thousands of black hole compact binaries containing a companion which is close enough to the black hole that the black hole actually sucks the gas out of the companion. We observe dozens of them, and most of them go through outbursts, and during the outbursts they can be quite bright. They can reach significant fraction of the Eddington luminosity. What makes them so bright? This is the accretion. Accretion of gas which liberates its gravitational energy on the way towards the black hole. So let's look more closely into the physics of accretion. There are three fundamental equations which describe the accretion disk, at least a thin accretion disk. This is the vertical balance of forces, where the vertical gravity is balanced by the force related to the gradient in pressure. And we have two formulae for the heating and cooling. Heating is related to the turbulent dissipation and is often assumed to be proportional to vertically integrated total pressure with the viscosity parameter alpha. The cooling comes from the diffusive transfer of radiation and scales like temperature to the power of 4 over the optical depth. What if the pressure is dominated by the radiation pressure, which is the case for the most bright disks which we are interested in? Then we can write down the formulae for the heating and cooling as a function of the radiation pressure in the midplane, and we see that the heating depends as the square root of the radiation pressure in the midplane, and cooling depends on as linearly with radiation pressure. What does it mean? That the heating responds stronger to temperature or the radiation pressure than cooling? It means that we can expect a runaway behavior. If we double the temperature at the equatorial plane, let's say if we double the radiation pressure in the equatorial plane, the heating rate will grow faster and the temperature will keep increasing. And it has been shown beautifully by Yanfei Jiang using local shearing sheet simulations. And what they observed is that the disk either the disk either goes over runaway collapse or actually expands to infinity. But what happens if we have a global accretion disk extending from the black hole horizon towards the companion star? Then one can expect so-called limit cycle behavior, where the presumed equilibrium structure of the disk is completely disrupted, and the disk evolves violently, and one can expect huge changes in luminosity, and the variations, the characteristic time scale of the variations should be of the order of seconds or hours. But for most of the observed black hole binaries, we see nothing like that. This is a line curve of one of the black hole X-ray binaries, which extends over a year, and the luminosity hardly changes at all. This means that, for some reason, the thermal instability is not operating in most of the black hole binaries. How does this picture, the simple argument which I have just given, change if we include magnetic pressure? So we can now write the total pressure as the sum of the radiation pressure and magnetic pressure. And we may introduce the magnetization parameter beta prime, which tells us what fraction of the total pressure comes from the magnetic pressure. And now you can easily imagine that if we perturb or change the radiation pressure in the midplane, then let's say we double it, the total pressure will not double because there is a significant component of the magnetic field. So the response of the heating, which depends on the total pressure, will no longer be so strong. And one can see that if magnetic pressure dominates the pressure budget, then we actually arrive at a solution which is supposedly stable. And this has been known and proposed and anticipated for a number of years, but it has, well, this idea has not been recognized because there are two major question marks that one has to try to answer. How to make a disk magnetized? The disk is so strongly magnetized that disks by themselves want to saturate at a level of, let's say, 10% of the total pressure provided by the magnetic pressure. And another question mark is, can it be numerically verified? Is it really the case? So let me briefly answer the first question mark, or actually give some ideas how we can make a disk magnetized. Shenin Bai and others have shown that if we thread local shearing boxes, local patches of an accretion disk by a large-scale magnetic field, either vertical or even better radial, then the saturation state shows much stronger magnetic field. However, one has to provide the large-scale magnetic field, and this usually requires effective advection of the magnetic flux with accretion, and this is supposed not to be efficient for thin disks. But maybe accretion above the surface or near the surface can help. There's another idea of making a disk strongly magnetized. During the hard to soft transition, when the accretion rate increases, the cooling radiative cooling suddenly starts to be imported, and the disk actually collapses down. So we lose radiation support, we lose thermal pressure because the disk cools down, but the amount of pressure provided by the magnetic field does not change by a similar factor, and we end up with a magnetically pressure-supported state. However, if it can survive by its own for a long time without extra non-zero net flux of magnetic field is a question that has to be addressed. But let's now move to the second part, which is the numerical verification of that. So there is a hope that the configuration, the setup of the large magnetic field can actually determine the magnetization of the system. So this is the experiment project which I have recently done. I simulated two global accretion disks in 3 dimensions using my own radiative code. And the simulations were initiated with 2 different topologies of the magnetic field, which was weak magnetic field, but which was enough to trigger turbulence and which was threading the initial torus of gas. One was quadrupolar, the other one was dipolar. If you pay attention to the red boxes, you can actually see that the magnetic field topology inside the box, so like local, is completely different. The dipolar field provides effectively net vertical flux of magnetic field. The other one, especially if you pay attention to the equatorial plane, provides actually radial flux of magnetic field in that region. So I evolved them as slightly super Eddington sources, super Eddington disks, which are stabilized by advection for some amount of time, and they evolved into respectively strongly magnetized system and weakly magnetized one. And then I used these equilibrium states, turbulent equilibrium states, either strongly or weakly magnetized, as an initial condition for simulating sub-Eddington, for simulating supposedly thin disks. And I did it by rescaling it down so that suddenly such a system is supposed to produce sub-Eddington accretion. And then I studied how the disk responds to this suddenly sub-Eddington state. And here are 2 animations which will show the evolution of the gas density either in the equatorial plane or in a on a poloidal plane. And the graph, the line actually shows the accretion rate over time. So one can see that the strongly magnetized simulation, which is shown on the left, is able to retain the equilibrium state, which corresponds to roughly 80% of the Eddington accretion rate. And very little change happens over time. However, the other simulation shows that the accretion rate decreases significantly, and the disk actually collapsed from a thick structure to a much thinner one. so thin that actually the magnetorotational instability was no longer resolved. So I had to stop the situation. This is a slide which summarizes the behavior. The strongly magnetized simulation stays around the same state for as long as the simulation was run. And actually the simulation was run for 20,000 gravitational times, which corresponds to 2,000 orbital times at ISCO. So for quite a long time. However, the other one definitely collapsed. It was not able to maintain the equilibrium state. Let's look more closely what is going on in both of the simulations. One can calculate the heating and cooling rates. This plot corresponds to the strongly magnetized simulation and shows with the blue line, the cooling rate with the blue line and heating rate with the orange line. And you see that over time, at fixed radius, the two follow each other. So there is a balance. There is a thermal balance, and the disk neither cools down nor heats up. It is a completely different situation in the other case, where almost from the very beginning, the cooling was exceeding significantly the heating rate, and as a result, the disk was losing radiation support and collapsing towards the equatorial plane. And you see that the black line shows the magnetization parameter beta prime, and you see that this is actually what was one of the ideas for making a disk magnetized, that once you lose the thermal support or radiative support, you become magnetized. But one cannot actually, I was not able to follow longer on this simulation because it was too close to the equatorial plane and too dense, and I would need much stronger, much higher resolution. So the summary is the following. I have simulated a strongly magnetized disk, which provided sub-Eddington accretion rate. And this disk was able to survive for a long time, so it was able to maintain the thermal equilibrium. The other simulation was not, but this fact does not prove that weakly magnetized are always unstable. It just proves that that this very simulation didn't want to stay at that given accretion rate. How can we provide high rate of magnetic pressure? Either through advection of large-scale magnetic field or by the collapse, which takes place during hard-to-soft transition. And what should we expect from such magnetic pressure-supported disks? Well, mainly we should expect that they will be thicker than the standard Shakura and Sunaev model predicts. And if we want to predict what the spectrum would like, it would be harder because the photosphere extends more into the hot polar region, and maybe it would also imply that the estimates, which are based on the Novikov and Thorne standard thin model, overestimated the values of black hole spins in the galactic X-ray systems. Thank you. Yes, so below and above the midplane. Well, exactly. The radial or the vertical? Okay, so above the equatorial plane, the loop goes like that. Below, it goes like that. So yes, the vertical net flux is effectively zero, but there is no symmetry in the radial flux. So near the equatorial plane, the fluxes actually sum up, and you have a strong positive radial component near the equatorial plane and negative components closer to the surface.
Yeah, this is beautiful work. I'm wondering now if you try to put this together with something like the systems that Joey Nielsen has been studying, like the heartbeat system. So there you do have some very interesting time behavior, and he relates what he's seeing to winds. The interaction between winds and the infalling material. Now, in this case, if we take your basic formalism and then incorporate winds into that, do you think you would have the best of both worlds, this type of disk description?
Well, so yes, in principle, if for some reason a given system is not able to advect large-scale magnetic field, or maybe this large-scale magnetic field is not provided by the companion, so there's nothing to advect, then one should expect violent luminosity variations like the heartbeat state. So yes, but the fact is that most of the objects, they are perfectly stable. So for some reason, systems actually probably they prefer the strongly magnetized state. And we need to understand why. I have just shown that it depends on the magnetic field which is in the disk. But why such magnetic field actually is formed or preferred is still to be investigated.
Thank you very much.
Thank you. That's a pleasure. Thank you for putting me in. Oh, I should turn it off before I say something stupid.
I think